Okay, can you hear me now? Great. So the point of this question was to find V0 and Vx through nodal and mesh analysis. So I thought this was a harder question because it's going to take a little while to analyze all of that. So the first step in mesh analysis, we'll start with nodal. And the first step for that is just going to be defining what we're calling all the voltages. So we'll start with V0 here, because they've already given us what V0 should be. Call this one V1, V2, and V3. So before we start with that, I'll just point out this is a voltage source up the top, right? So when we have two nodes separated by just a voltage source, we can actually make a supernode. So we'll start with that equation. And all we have to do is say V2 minus V3 is equal to 4I. And then we'll start with the nodal analysis. So if we start with V0, we can look at the current flowing in, which should be 2 amps. And then we can make that equal to the currents flowing out. So the first current flowing out would be across the 3 ohm resistor. So we have VO minus V2 on 3, then V0 minus V1 on 2. That's the first equation. The second one, we just do the same thing at the node V1. And for this, I'll just assume all the currents are flowing out just to make it really easy to write it. So we can start all of them off with V1 minus V2 on 5. And you can just always write it in this form, just assuming the currents always flow out. It doesn't actually matter which way you assume it does. In the end, the math will all work out to be the same. Then we can do it for the supernode. We just have to look at what comes in and what comes out. So we have, assuming everything goes out, V2 minus V1. So that would be these two. And then if we did this part, it would just cancel out with itself. So we can ignore that and just look at the current flowing out here. And that should describe V2 and V3 as one block. So then we can go plus. So does everyone understand so far what's happening? Okay. Yeah. Okay, cool. So question from online with 4IO. Well, we know I0 is just the current through the 5 ohm resistor. So we can say V2 minus V1 on 5, just from nodal analysis, just from Ohm's law there. The voltage across the resistor divided by the resistance. So then we can say V2 minus V3, 4 on 5, V2 minus V1. So is that all good so far? And then this gives us a lot of simultaneous equations to solve, which can be a bit difficult, but we'll start by just simplifying these down a little bit, I think. It's this one, we can just say that so I think getting rid of V3 first is a good start, just in the supernode to simplify that down, and then we'll just have a normal simultaneous equation to solve. So from above, we can work out what V3 should be. So we can simplify this down to V2 minus V1 on 5, 3 plus, and does anyone know what V3 would be equal to? Okay, so we'll just look up above at the equation we had from the supernode to start with. And then here we should be able to say 4 V2 minus 4 on 5 V2 minus V1. Which isn't very nice. And then we just have to simplify this down. So I might save a bit of time here to grab what I've already simplified. Yeah, so this should simplify down to V2 minus V0 on 3 plus V2 minus 3 So then now we have the 3 equations in terms of V0, V1, and V2. So all we have to do now is just solve them for any part and plug it back in. If you want, we can go over how to do that, but I'm hoping you all know how to do that from high school. Just solving large simultaneous equations. It's a big pain, but it is something you should definitely practice for the exam. And then, because the question asks us to find V0 and Vx, V0 should be fairly easy to find, but can anyone tell me what Vx would be? So, yeah, perfect. So we just subtract those two to work out what it is. And now the second half of this question. Actually, I should ask, does anyone want me to actually go through and try and solve those? Or I assume that might get a little boring to watch. So now we can start looking at how to do this with meshes. Yeah. Yeah, that's a good question. The way those pluses and minuses are drawn, current would be current would be flowing in that way. But if we write the equation this way as the current's flowing in, we would just end up with that section becoming negative. So it doesn't matter which way we assume the current flows, because if we just write it this way, it'll be a negative current flowing in, or in this case, you probably end up with a negative voltage for Vx. So when you define those things, it just ends up putting plus or minus how it is. You can do it however you want, as long as you end up being consistent throughout. Yeah, and that's what I wanted to highlight as well for V1, is that I just put V1 at the start for everything. Obviously, current isn't flowing in from everywhere. One of those would end up being current flowing out, but it makes it a lot easier to write the equation. Let's do the same way as minus. So again, it doesn't matter which way we make the currents going. I'm just going to say that they are all going clockwise, because that makes it very easy to keep track of. I4. So can anyone tell me where they think the supernode is going to be, or super mesh? So again, whenever we have like a current source for meshes or a voltage source for nodal, that's going to make our super mesh, because we know from the 2 amp source that I3 minus I2 is equal to 2 amps, just by looking at what's flowing into that and what's coming out. And so because we know that, we don't have to write 2 equations for this and then a second one for that. We can just look at them combined and go around the outside and make that our super mesh. Does that make sense? Good. So hopefully if I just go through the super mesh, it'll start to make a bit more sense. So if we define just looking clockwise and just adding up all the voltages, we know that I1 times 1 will be the voltage across the 1 ohm resistor. Then we have 2 I1 minus I2. That's 5. This makes sense how I'm choosing the positive and negatives so far. Yeah. Just a question. Why is it not? Why is it I2, not I1? Thank you. It should be I1. I've just written the wrong thing down there. Sorry. The 5? Yeah. So the way mesh analysis works is that we're going along in a loop and we're adding up all the voltages together. And then they should all add to 0 because we've formed a loop. So what the first one there is, it's I1 times the 1 ohm resistor. And then we're doing I1 minus I2, which is the current flowing in the direction of the mesh, multiplied by the 2 ohm resistor. And then again, we've got I3 minus I2, which is the current flowing in the direction of the mesh, multiplied by, that is a 3 ohm resistor. Thank you. Yep, 3. And then what's the current going to be flowing through the 4 ohm resistor? Anyone? Perfect, yeah. And then plus 1. And that's all equal to 0. So then we can go through meshes I2 and I4 next. So we have so for I2, if we start at the 5 ohm resistor, we can just do 5 I2 plus 3 I2 minus I3. Yeah. Minus 3 I3 minus I2. It depends on how you define the current flow.
Yes,
so
if you're doing the I2 mesh, if you're doing plus I3 plus 3 I2 minus I3, then in that case, you do negative there.
Yeah, 3 minus I2.
Yes, so wouldn't there be a sign change now? Like either in I2 or either in this mesh. Either like minus 3 I2 minus I3 or like minus 3 I3 minus I2.
So if you wanted to do that, you'd actually move it to the other side. Because on the left-hand side is everywhere there's a voltage drop. And on the right-hand side, we can put everything where the voltage, so it should be negative if the voltage is increasing. So if we wanted to, you're right, if you wanted to assume the voltage is increasing from that, as they've done with the minus and plus, we'd have to swap the way the currents are flowing as well. So we could go minus 3 and then assume the current is flowing down, right? If we're assuming it's that way. So then that would give us I2 minus I3. But instead of thinking about that every single time, and where you can end up making a lot of mistakes, I like to just assume that every single one is the voltage drop and the current is flowing with the mesh. Because then it saves you a lot of time thinking about that. And we can just start it off with, and we can do it that way. But both are totally fine. Does that make sense? Or am I confusing for the exam? Okay. Yep, just do whatever way you're comfortable with. This is how I prefer to do it, but both are totally fine. Cool. So then for 5, 3 I2 minus I3. 2. Hopefully you see for this one, it helps a little, make it a little bit faster because it's always just I2 minus something. Let's see, minus I2. That. Cool. And then we would go through I4. So here, what is I0 going to be? Sorry, Yeah. And then we can just say, so we would have 4i0 plus 4i4 minus i3, we assume plus minus there, is equal to 0. So then we again have here, instead of having 3 equations at the moment, we've got 4 because of the super mesh. So we would have to find one of these and just simplify it down to get 1, and then we can solve it normally. Do people want to see me going further with this, or just moving on now and we can look at things, other examples? Is that a nod for going forward? Okay, cool. That's not the most interesting example, but I think it's a good start. So this question has a little more to it. Here we want to find what ZL should be to get the maximum power flow. So in that case, our first step is going to be to calculate the Thevenin equivalent, so the Thevenin resistance. So if we remember how we do that, we're going to, in this case, because there are no dependent sources, we can just disable the independent sources and then have a look through the 2 nodes. So we can actually redraw this as minus J10. Now, is a disabled current supply going to be an open circuit or a short circuit? Okay, and can you tell me why? Yeah, perfect. So if there's no current flowing, we model that it's an open circuit. With voltage sources, 0 voltage is a short circuit. So now we just look at the impedance from these 2 nodes. So that's going to be the top half is 30 minus J10. And that's going to be in parallel with the bottom half, which is 40 plus J20. So this you can do on your calculator fairly easily, because you should all have complex calculators at this point. Oh. And that simplifies down fairly nicely to 20 ohms. Then we know that ZL for maximum power transfer should be 20 ohms. I'll give you guys a second to do that if you want to take it. Yeah. Sorry. I'll sneak over that when it needs. I think so. Yeah. Hopefully you are all good to do that. It would just be the 130 minus J10 times by 40 plus J20. And then on the bottom, you would add them. So you can just enter that in the calculator and it will give you that result. Then because that's the definite impedance, our load should just be the complex conjugate of that, or in this case, since it's purely real, it's just the same thing. Then the next part of this question is going to be working out what the Thevenin voltage is. So how do we calculate the Thevenin voltage? Yeah, so that's a good way. Skip a step there, is that we have to, for finding the Thevenin voltage, we want no load. So we just make it an open circuit. And for Norton current, again, that would be our short circuit current. So we'd start with a current divider. So that's going to be 30 plus J20. What does that work out being? minus J10, and that will be the current through our left. And for the right-hand side, we just do the other way around, where we have 40 minus J10. And it's always the resistor you're not looking at to work it out. And just to skip simplifying that down. We're going to have 2.55 So now that we know that, we can actually look at making this a mesh, where this can just be V Thevenin. Let's make that one plus and that one minus. So then we can go V Thevenin. And we need to work out what the voltage across these two is, right? So if we want to assume we need to pick one side to be positive, one side to be negative, right? So let's say that and that all the way around. So that's going to be let's put this one the other way around so it can be on its own side. So we can go minus J10 times, this should be minus I1, right? Because if that side is positive, can't go the other way. Or we can put that minus up front. Does that make sense? Why this one is minus here? So we're assuming positive that way. Cool. And then for the other one, that's just I2 by 30. So we'll find the Thevenin is equal to J10 I1 plus 30 I2. And then we have what each of these are. So you just plug that into your complex number calculator. And does anyone want to say what that gives us? Yeah, you just plug that in, it should give you this. So what would the next step be to work out the power in the load? Does anyone know the formula? Yeah. So that's the formula. But if you don't remember that, all you have to do in the exam is just think back and draw the circuit again. So in this case, we had 20 ohms. And this is 70. So to do this the long way round, because most of these are not too hard to work out if you do forget the formulas, is that we could work out the voltage on this one would just be half of that. So the load is going to be 70.84 on 2. Then to get it in RMS, we divide it by √2 again. And then power in your resistor is V squared on R. So that will give us this. Which is just an expanded version of that formula. I hope it helps to see a little bit where some of these come from. Okay. Are there any questions about that? Calculate. formulas used to calculate I1 and I2. So that's the current divider. So the most basic example. We have R1, R2 here. The current through R2 is going to be equal to so for the current divider, that's the formula, and it's going to be, make sure that what you're looking for, the current through that, you actually have the resistance of the other side, which can be an easy mistake to make in the exam, so just double check when you're doing that. Cool. Okay. Is everyone okay with that question? Great. All seem to be. Let's move on to the next one. So I wanted to have a go at the op-amp question, which was 2020 Q3B. We draw that out. Okay, so for this question, we know the first thing it tells us is that V in is 500 Hertz, and it has an RMS of 500 millivolts. And it wants us to write it in time and phasor form. So does anyone know what the how to find the amplitude of this from RMS? Yeah. So it's always just times √2 for that. So Vn √2 by 0.5. Doesn't matter if you write cos or sine. And what should we put in here now? Yeah. Okay. So we'll just, it's just 2 pi ft. That's what always goes. All right, top. So in this case, we know that it's 500 and t. And important thing, volts. We have to remember to keep the units, because that is an easy way to lose marks. Everything really have a unit, so you want to keep those. And then how would we change this to phasor form? Yeah. Perfect. that's going to be 0. And again, volts at the end. So then the next step is to work out what the output voltage is. So the first thing we're going to do is look at these capacitors, which have 31.38 nanofarads. And we're only analyzing this at one frequency, so we can just work out what they should be, which is minus J10K. Yep. So what do we always do with op amps? Like the golden rule. So the golden rule of op amps is that these two voltages are always the same. So we'll call this negative, and we'll call this V out here, which means that this one is V out, and this is also V out. That leaves us with one more node to look at, V1. With op amps, it's almost always better to use nodal analysis, just because it gives us two nodes that are exactly the same. It tends to work out a whole lot easier than trying to do meshes. So to start with this, we'll have a look at V1 and write the nodal equation for that, and then have a look at this V0. Because that should relate V1 and V0. So we can say on 10K. So that's just the current through the first resistor, the second one, and the top capacitor. Then to take a look at relating V1 and V0 together, we can say V1 minus V0 on 10K is actually just going to be equal to V0 minus 0 . We'll write that the same, keep it consistent. Yeah. So then we can relate V0 and V1 here. So we'll just multiply everything by 10K to get V0 minus V1 plus J V0. And then we can say V1 so then we just take a look at our first equation, and we'd sub this back into equation 1. So if we did that, multiplying it by 10K again, we have V1 minus V in, V1 minus V0 plus J. Just sub these in, and that should tell you what V out is. think, yeah, just because this is the first phasor one, I might actually go through that. So if we sub that in 1 plus JV0, simplify that to then substituting all of that in. I just use the calculator for this again. We get V out by 2J is equal to V in. Yeah. So how would we work out what the final answer is as a phasor now?
Just a question, how do you get the second nodal equation?
The second nodal equation? Yeah. So that was taken from this part right here, where I looked at V0 at the non-inverting input of the op-amp. Cool. Yeah. Thanks for relaying the questions too. We should like this one. Then basic phasor math, that would be equal to 0.707 on 2. And for the angle, it's 0 minus 90. And that's our answer for the app. Then the final part of this question is going to be to take a look at how much current, I'm sorry, is to take a look at the average power absorbed by the speaker, which we're just representing as an 8 ohm resistor. So again, we can just use the formula of V squared on, yeah, so that'll just be V squared on R will give us the power. So if we take, and then to go from the peak to peak, so the peak voltage of the amplitude to RMS, we divide it by √2. So that's going to be 0.354 on √2 squared on 8 will give us our power. Which is 7.8 milliwatts. How is the pace for everyone so far? Doesn't seem to be a whole lot of questions, so yeah, that's perfect in the questions. We don't have to worry about current going into an op-amp because we can assume that's 0. Yeah, so is this a good speed to be going at, or faster, slower? Any specific topics there's people are struggling with? Cool. If it's all going well so far, I will move on to this step question. So the premise of this question, which is 2019 QB, Q2B, is that initially we have 0 voltage. The amplifier breaks at t equals 0. So from t equals 0 to 30, the switch is closed. And then after that, from the switch is to ground. So then the question just wants us to describe for the first 60 milliseconds, find the equations that will tell us the voltage. So we'll probably start off with a formula here. Does anyone know what that should be? So we'll start with, yeah, step response formula. Do you know what that is? Great. So e to the minus t on tau. So then what is V infinity going to be when the switch is closed? So, sorry, not quite. So when the switch is pointing up at VA, I mean, what voltage will be across the capacitor? Yeah, perfect. Because at infinity, we can effectively make the capacitor just gone. It'll, at infinity, it will just be a short circuit. So that'll be VA, which is equal to 15 volts, given the question. And then V0 is going to be what we started off with. And because the system started with it closed, so with the switch pointing to ground, it should just be 0 volts. And what should tau be here? Yeah, so that's what it has initially. And initially the circuit was the switch was down here, we can assume at the start. Do you all have access to the questions? I think they should have been shared. Yeah. Yeah, cool. Once I have the answer scribbled all over them. So what was your question?
I was just thinking of access.
Cool. And yeah.
So for t less than 0, is it connected to ground?
Yeah, so we can assume that from what they give in the question. So then tau is going to be here, RC. And we know we have 4 ohms, 1,000 microfarads, which is 1 millifarad. So that's going to be equal to 4 milliseconds. So our final equation is going to be I have these backwards. -15 minus and that's going to be the answer for part 1 of this. So then to do the second part, where we wanted to find all the way to 60, because this will just be between 30 milliseconds. We need to find it for 30 to 60 milliseconds when the switch closes to ground. So for this, we can actually make the assumption that it reached all the way to 15 volts, because tau was 4 milliseconds. So we can say at 5 tau, we've effectively reached infinity. It will never all the way reach there, but at 5 tau, we call it close enough. So if we say 5 tau, 5 tau is less than 30 milliseconds. We can just say if you wanted to actually calculate this, we can use the formula we had before. And I believe that gives you 14.99 something. So we can, again, if you do it that way, you can say it's 15. And the reason we're doing that is just to simplify this whole process a bit. So now instead of doing the step response, we're just going to look at the natural response. So this is just a little bit less. So you can choose to memorize this formula, and just plug it all in here. Or you could do something very similar based off the previous formula, where we know here that the infinity would be 0 if we did it that way. So you can choose to memorize just this one main formula and use that instead, which I'd probably recommend because the less things you have to remember in the exam, the less likely you are to forget things. So just being able to work these out, if you forget the power formula for maximum power or what the natural response is, you can just use the step response and work it off that, because here the infinity would be 0. And we know that's 15. So that would give us the same thing. Does that make sense so far? Yep. Yep. Thank you. Cool. Yep. A plus, oh, sorry, that should have a minus out the front. P0 minus. So this should be a plus. Yes. Okay, no, then, yeah, sorry, I wrote this differently to how you normally see it. Yeah, so are you used to seeing it with a plus and then this way around? Okay. Yeah, sorry to confuse people there. So that gives that one is 15. Yeah, that works. Okay, cool. So any questions so far? Yeah.
I didn't really understand like how you got to 15 volts to be like at 30 or something. Like that.
Yeah. So I used the formula we had before, and which was this one. So if you just plug in t there as 30 milliseconds, you should get something that's 14.999. And we can say that's tau is still. So that, yeah. Yep, so tau should be 0.004. That is a very messy tau by me. I will write that nicer. So did that make sense now? Awesome. Awesome. Yeah, so we're an hour into it now. If everyone wants to stand up for a few minutes and wave your arms if you feel like it. because it's a long time to just sit down listening. If you're all very enthusiastic, we can keep going, but I figured a 5-minute break might be nice for everyone.
Just gonna take a photo of this.
Yeah. This one is different from the one here. At least it's like
So yeah, so I got a little mixed up there. So that's how I have normally written this. Yeah. And so that one should then be V0. V0 infinity there. So
What does this do? Sorry.
should be that.
Sorry. Okay, so it's V0 minus V infinity.
Yeah.
So something else.
Yeah. So for the first one, I wrote it this way,
Yeah, it's V infinity minus V0.
but there's a minus up the front there.
Yeah.
Yeah. So then I got told that's not how you normally see this formula. So we can just swap it around to look this way. Effectively,
But
what
like,
we've
where is
done.
the sign change? Like here it's positive and it's negative. So is
Yeah.
it because of this? Like V0 is supposed to be here and V2 is supposed to be there?
Yeah, so that it's the same formula between them. It's just we've effectively multiplied the minus
Yeah.
through. So like the V0 still ends up being positive total, the infinity is still negative total. Is that
Yeah.
awesome?
It's for the separate response, right?
Yeah.
Thank you.
Hey,
So when you're doing the voltage slide, they technically in series.
so that was current divider.
Yeah, yeah, they're kind of close. Yeah, I was looking at them like, I thought they were. I'm assuming the answer is.
Yeah. So just grab something when you at it. So you're saying, so when we look at the definite, these two are in series, and these two are then in parallel with these two.
So then,
Like, so that's
then
the,
how are we only letting them bond? Shouldn't it be like the equation of like,
let's just get that up.
see if they're in parallels and multiply both of them and then add both of them.
Current divider formula. So that's what I tried to scribble off to the side.
Is this all that? Has always been using like the current source or volume source, whichever, and then it's either 1/1 and then you're adding them all together, or like R1 times R2, R1 plus R2.
Yeah, okay, so she has used this formula.
Yeah. Wait, how can we just do? So you're losing like a whole resistor on the top that's being multiplied.
Yeah, so we can just scribble that out. So that would give us like 1 on R1. So we just multiply by and that should give us,
Normally it's just, oh
yeah. I'll put it that way. Yeah. So it ends up being the same thing.
Yeah, she'll either have R1 times R2, R1 plus R2, or then 1 over that plus 1 over that, which is 1 over which. I'm just confused as to why we've been using that other equation with R1 times R2 over R1 plus R2.
It's R1 times R2
Over
over.
R1 plus R2 times, and then that all of that times by the source.
So can you write that down for me?
So is
Yeah, no, so that's just the
So this formula is,
and it can only be
R1.
used if there's two.
Yeah.
Yeah, two in parallel.
so that's for them in parallel.
Yep.
So this would actually, if we just scribble out a quick circuit, that is the formula, because that's just IR, right, effectively?
Yep.
So that's going to give you the voltage there.
Yeah.
Yeah, that's a totally valid way to do it. You could work out the voltage and then from there work out the current, but your current divider formula.
Maybe I'm just getting that because normally I just do like 1 over 1 over and then just like do that for everything, just so I can just remember that one. It's just easier doing it that way. But then I was just remembering this from like something was not clicking. So yeah, that makes sense.
Yeah, good to ask about it. Because,
Which I'm not going to use it anyway, but I was just confused.
Yeah, fair enough.
I'm just going to use the same one I've been using.
I'd rather someone asks than I've told everyone the wrong.
Yeah.
In exams, as I said, the way you're comfortable with is the best way to do it.
Oh, I'm not comfortable with exams also.
Yeah,
Thank you.
It is there. I don't really teach us a lot. I think it's like orbital thing.
Most times just do something.
Yeah. Like we avoid
I never need to.
that's it's like a maybe not yeah.
Maybe it's on. It's up to you.
Yeah, I don't.
No.
Yeah, okay, sure.
But like,
Oh, but I guess not every.
yeah.
Yeah. Quite confuse them. Was that then? Move on to some hopefully easier ones. Cool. So I don't understand why 30 ohm is in series with minus J10 ohm. So 2019B. Yeah. So 30 ohm, can you hear me, Kiyan? Great. So I'll just go over this quickly for you. That the 30 ohm is in series with the minus J10, because when we look at it this way, at the start. The path for currents is this way for one, to the top half, and the bottom half, it will be going similarly here. So that puts the 30 and minus J10 capacitor in series together to find the Thevenin equivalent resistance. Does that make sense? And then for the next part, when we did the current divider, that's where we can start looking that way. Does that answer your question? Yeah, perfect. Yeah, this is a bit of a tricky question. I thought it was interesting. Great. Okay. Let's get back into this. Okay, so up to everyone what we want to go through now. Sorry, could I get everyone's attention again? So excuse me. Thank you. So just want to start it off again. So we can go through a power question, which will involve some Thevenin, a more complicated Thevenin one, or there's a superposition question. So up to people here what we want to start off with. Easy. Okay. So what's going to be the first step here? If anyone wants to say, find R load. Yeah. So what should our inductor impedance become? Sorry.
48
pi. So that should be so now that we have this, we're going to work out the Thevenin resistance, assuming our load is now open circuit. Without that, and we're going to disable the voltage source. So again, is that open circuit or closed circuit? Great. So if we redraw this now, 20. So then Z-thevenin should be 20. Now we can just work that out with the calculator. Cool. And can anyone tell me what that is in phasor form? So that should give us 76.3 plus. Got normally. Yeah.
So 76 plus 3 digits, so like 84.
79J. We could just say 0.8J. It's probably better. So yeah, if you got that, that would be good. Awesome. So what do we think our load should be now? Yeah. Which is actually just going to be the same as what is before in the phasor. So we should have our load. And that's what our load should be. Yeah. If our load was instead like Z load, and we could make it a complex number, what would we make that? Would it be the same thing? Yeah, great. So then we'll move on to the second part. And find the maximum average power. So how does everyone think we do that? Yeah. So we'll look at it open circuit. So now we'll just do a voltage divider here. So we want the voltage across that 200 ohm resistor. So we'll put 200 on the top. And then we'll put all the resistances there. So that'll be 20 plus J150 plus 200. And what does that get us? That should be something that you can just put into your calculator and find out. Sorry. 48 pi is 150.79. So rounded a little bit, but yeah. So now that we know V-Thevenin, and we know Z-Thevenin, we know what our load is. The next thing we can do is work out what the load would be. So that's just going to be another voltage divider of RL, RL. V-Thevenin. So if we remember what RL is, it should be 20. So then this will just give us 49.25 minus 59. And now we can work out the power across this resistor. So power is V. Yes, thank you. That was the previous question, was 20. Yeah. So we should have this. Yeah, that should give us the same V load. Power is V squared RMS on R. Then all we have to do here is find V load in RMS. So that'll be 49.25 on the square root of 2 squared on 114.06. And that's going to give us 10.6 watts. Does that make sense to everyone? Yeah. V-Thevenin? Yeah. So to find V-Thevenin, we just looked at the circuit with the load being an open circuit, and the voltage there is going to be V-Thevenin. So then Looking at this circuit, that's just a voltage divider. Any other questions? Okay. In that case, we'll move on to the next question, which is 2019 term 1, question 1b. If there's ever more questions that pop up, feel free to just stop me and make me go back. So this question is about a hot water heater and just finding the power through it. So for this one, we have both a voltage source and a dependent current source. So how does that change finding the Thevenin voltage? Or does it change it? Yeah, so because if we have just a dependent source, then we start needing to put in dummy sources and doing it that way. But having both of them, we can find out the Thevenin, fine. But to find out the resistance, that's where it gets a little bit tricky. So we can just do the Thevenin resistance totally normally. Yeah. Sorry.
Yeah, I just wanted to see the answer to this question.
So let's have a go at part I. So should we use Thevenin? So should we use mesh analysis or nodal here? Do people think? Because we'd have two nodes if we did it. There'd be node 1 and node 2. Or if we did it with mesh, we'd have I1 and I2 there. But it's probably easier with mesh because we have this nice source right here that's going to let us make one big super mesh. So if we go through this way, we can get minus 230 because we'll look going around clockwise like we normally do. We're going into the negative terminal, so that will give us negative plus 5 I1 plus 100 I2 10, thank you. 10 I2 plus 10 I2 here because this is assumed open circuit. Equal to 0. And then from the supermesh equation, we have that dependent current source. So that is I1 minus I2 is equal to 0.5 Ix. And what should Ix here be? Yeah. Cool. So then we're just going to plug that back into the first equation. And we'd want to find I2 first, because that's what's going to tell us the voltage across the 10 ohm resistor. So we'll try and get it all in terms of I2. So we have 230 is equal to 5, 3 on 2 I2 plus 20 I2. Then we put that into calculators. Thus I2 is equal to 8.36 amps. Then phi Thevenin is going to be the voltage across this resistor here. So that's going to be 10 times I2, so 83.6 volts. So how are we going to find, is everyone okay with that now? Everybody following? Awesome. Then let's have a look at finding the resistance we should be using. So how should we do that, do people think? Great. Yeah, so because we have that dependent source, we can't just look into the node, look in from the 2 points and see what it should be, because we'd have no way to quantify that dependent source. We can't ever turn it off. So we'll try to find short circuit current. So let's simplify this circuit. We want to know this current. But something really nice happens here. Because we've made this a short circuit, the resistor next to it won't have any current flow through it. And then the dependent source, the current that flows through that, is half of the current flowing through that resistor. So if there's no current flowing through that resistor, there'll be no current flowing through that dependent source. And if there's no current flowing through the dependent source, it'll just look like an open circuit, right? So because they've made that so nice, it looks like a hard question, but it simplifies down to this. 5, 10, and 230 volts. Then we can find out nice and easily what the short circuit current is going to be. It should be 15 amps. Does everyone understand how that worked out? Because that's got a bit of a trick to it. Yeah. What is? Like this bit, I can write that a bit. Yeah. So if you can't read these, I can make them bigger for you or take some extra time, draw them neater. Yeah. Is that better? Cool. So now we have that. What should R7 be? Sorry. Yeah. So that's going to be 83.6 on 15.3. That gives so then what's our load going to be again? Yeah. So now and again, make sure you write the units. So this is in ohms. I don't think INMAR would be too mean about that, but it's always good to make sure you have it. Yeah.
In case you didn't have a dependent source in this question, how would you get the heater resistance?
Yeah. So this method would still work. Yeah. Like you could do, if you did this, you'd waste a little bit of time, but it's totally fine to do. If that dependent source wasn't here, so we had just this, what we'd want to do is, oh, sorry, I'm like, if that was an open circuit, I mean, yeah. Sorry, if this was a short circuit here, yeah, if that was a short circuit, we would never have any voltage or current at the 7. Yeah. So was that your question? Or yeah, so if this was just like an open circuit, yeah, if we assume that's an open circuit, or even if it's just a resistance, we'd disable the voltage source. So it's a short circuit. And then we just look in from the 2 nodes and simplify it. So the same way as we did before, if I just take that. So if this is what the circuit looked like, instead of that dependent source, we'd just short circuit that voltage source. And then we end up with something that looks like this. So if we call this R1, R2, R3, R4, we'd have to simplify this down. So we could start by combining R1 and R2. So they'd be in parallel. So that's R1. So then you get this. And then hopefully we can see just by looking at that, we'd have what? R3 plus we get that equation. But yeah.
In case we had like a independent voltage source there instead of the 0.5 dependent source, that would short circuit.
So if here we had a voltage source,
Yeah.
just like a not independent, sorry, an independent voltage source. Yeah, that would just become a short circuit there. So it would then just be R3 parallel with R4. Yeah. Would you guys appreciate a quick refresher on all the different ways to calculate Thevenin equivalence? Yeah, okay. So the main way we've already covered is just disable, or if it's only independent sources, you can look at it to find the Thevenin resistance. So both. Yeah. So for this one, if it's only independent, you can simplify the circuit down. If you have both of them, you can't disable the dependent sources because that would lead to really funky things happening. They're not a set point. So you have to find the open circuit on I short circuit is equal to R Thevenin. And then if there's only dependence, that gets a little more tricky because you can't look at it and see it. And your short circuit and open circuit will always be 0. So we need to actually add a voltage or current source. And so if you were to add a 1 amp current source, you'd then look at the voltage across it to work out the effective resistance there. And then because it's only dependent and resistors, V Thevenin and I Norton would be 0. So does that make sense? Okay, cool. Because that's an important thing in it. That definitely confused me for a little while. Cool. So last part of this question is to find the maximum power. So we had R Thevenin 5.45. So I'll just do this one with the formula. So that should be C Thevenin squared on 8 R Thevenin. So then we can just plug that in. Wait, sorry. This is 4 because it's not RMS. Yeah. So then that gives us 320.8 milliwatts. Yeah. If you ever aren't sure about this formula, you just work out the voltage across it. So we know that the V load will probably be equal to V Thevenin on 2. So then if you just use the standard formula, V squared and R, that gives you V Thevenin on 4 R Thevenin, which is where that comes from. There's one more superposition example to go through. Would you want to do that or just ask any questions you have about anything really? If there's questions, just throw them out. Otherwise, I'll start working on the next one. Yeah.
You know how you did mesh, super mesh analysis on like in the first part?
Yeah.
I don't know how that's.
super mesh. Yeah, so because of this current source, we use super mesh and super node when we can just write a formula for the two of them very easily, because there's a source between them. So for this one, that source tells us that I1 minus I2 is equal to 0.5 Ix. You could do these two separately and then combine them with that formula. But because we know that, we can just make it one big mesh. And it's the same thing for nodes, where you just, if there's ever a voltage source between them, you just make it a super node. Any other questions? Okay. If there's no other questions, let's give this one a go. So for this one, we want to work out the current flowing here into this resistor. So we have 1 ohm, 1 Henry, 1 ohm, and 1 farad. So does anyone know how we'd start this question? Yeah. Okay, so what frequency should we use to do that?
Sorry.
What frequency should we use for that? 2. All right, there's also a 1 hertz. So there's also a half a hertz here. Yeah, so we'll turn off 2 of them. So voltage source again, that's going to become short circuit, and we won't bother with what's on the other side because it won't matter as there's a short circuit here. Yeah. This one actually has a frequency of 1 hertz because you have to actually tell even the frequency. So here we have omega is equal to 2. And if we remember, 2 pi f is equal to omega. So then here we can say f is going to be 1 on pi. Right, does that make sense to everyone? And then Z inductor, it's going to be J omega L. J2. And then the current is just going to be 10, 0 divided by 1 plus 2J. Then we'd just get this, put that into phases on the calculator, and that would tell us the first one. Then we'd disable the other sources and add all of them up together. So I might stop here and let people ask questions, or would you be more interested in finishing this example? People want to see this, all good, but it should be very similar to what we've done so far. We'd just get this, yeah, that would give us 4.47 cos then you do that again for the other ones. So if we do one more example here, looking at just this way. We can say here that that capacitor becomes an open circuit, inductor becomes short circuit, and we end up with just a 1 ohm resistor. So that's going to give us -8 amps here. All right, because the current will actually flow the other way. So our 8 amps. And then you do the last one and add them all together. Cool. Any questions? Are people following this example? I'm not sure how much practice you had with this. Cool. Yeah, I'll just hang around here for a while and answer any questions people have. Yeah.
What happens when only the sources on?
Yeah, of course.
Thank you.
Yeah, if you want me to just finish this example, I'm happy to. So we will disable the other two sources. So whoops, this is going to become short circuit. So will this one. Cool thing happens here is that because this is the short circuit, the voltage here will be 0 volts, right? Which means there will be no current flowing there. So that should have no effect. So then our final thing will be to sum this one and this together. And that will give us the final current.
Sorry, I don't get the answer. Why would it be bad for next?
So you don't get why it's 0 volts here.
No, I
Oh,
get
sorry.
why it's 0, but then why does that make the correct current?
But it's okay. So if we call this one, let's just call it V1. The current here, we call that like I1. I1 is equal to V1 on 1 plus J omega, right? Because V1 is actually always 0, this will always be 0. Yeah, because the other way to think is like a current divider, where some of the current will flow this way and some will flow that way. But because that one has 0 resistance, all the current will actually flow that way.
Oh, so if there's like in any question, if it's a current source, will it always be 0? Technically, will always have the 0.
Yeah, so if there's,
Looking for IO, which is on the other side, there's no current, so
yeah,
That's
Right,
facts.
so it's just the same in any scenario.
Okay.
or just-
because there was a voltage source that got short circuited because you did the superposition and switched it off. So then obviously it's
Yes, that I get that.
so if you have something in parallel with just a wire, there'll never be any current flowing through it or any voltage. As was being said, like we do have a current through here and here. There would be currents there, just not over there, because that's all effectively in parallel with the wire. So it'll still have a total resistance of 0. Cool. So yeah, so the final answer for that with superposition, we just add everything we get together. So that's going to be 4.47 cos 2t minus 6 degrees minus 8 amps. Any other questions about that? How I got like this part maybe? Or... Awesome. That's pretty much everything I wanted to go through. So yeah. Scroll down just there. I'll hang around here for a little while, answer questions. All good. Yeah. And if you do have any questions leading up to the exam, do you know the SuperELEC Discord? It's probably a good place to ask.
Nice plug.
It's where you'll get an actual answer. Yes, it's been served. It's
Can I
Okay.
ask you about this question?
Okay, so that was this one. Yeah.
So I was wondering why. I'm sorry. So VTH, we're trying to find the voltage at these nodes, right?
Yeah.
And is this ground at the bottom? Because like, why was it this times the current instead of this one times the current?
So we could have looked at the bottom. So this is using KVL, but like in a loop, it always adds to 0. Right. So I'm treating this part as the loop. I could have very easily made this the loop.
How was it?
Right?
How was it? Manageable?
Oh, where did that jump to?
Yeah, real bigger one because it's like because if you do like all this AC stuff recently, some of the stuff
Oh yeah, it's like the two.
Yeah. So we could have had a look this way and found the voltage here and use that one. But I just chose to use the top.
Okay. So it's just KVL at the top part. Oh,
Yeah, just one mesh.
thank you so
Okay,
much.
cool. Hey,
Sorry, we were a little bit obnoxious. I
all
was
good.
just-
It's nice to see people not just dying over exams.
So for this one, when you were solving part two, you found the power
to like a system, like I don't remember